Hi there, guys. My name is Wilfrid, and I'm a senior math tutor. And today I'll be covering 9 questions related to functions and algebra. A little bit backstory upon myself. I graduated from McMaster with a major in biochemistry and minor in mathematics. And if you have any other issues with any kind of calculus or mathematic problems or any kind of concepts, please submit them to OneClass and we'll get to them as soon as possible. But other than that, let's just jump right into it. Okay, so the first question, they don't really have a question that they're asking, but the question is very clear. So given that this graph of a function, so they didn't give us the equation of the function, they just gave us the graph. They want us to identify the open intervals on which the function is increasing, the function is decreasing, the function is concave upwards, and the function where it's concave downwards. Okay, so I'll go into a little bit of detail on how to do it mathematically and computationally, but I'll also be explaining how to identify what areas of the graph are increasing, decreasing, concave up, concave down, and where the point of inflection is. Okay, so let's start with A. So they're going to ask us to find the open intervals on which the function is increasing, okay? And there's a difference between what an open interval is and a closed interval is, okay? So if we had an open interval, we would use round brackets as the notation, okay? And this means that this interval includes all the values in between A and B. However, it does not include A and B, okay? So it does not include A and B in interval. Okay? So a closed interval, on the other hand, would be a square bracket, and that would indicate that the interval includes let me write no A and B. So that means that A and B are in the interval. Okay, so that's what it means by open interval, and we're going to use these notations to describe it. Okay, so the first two questions, the option A and option B, or part A and part B, is describing the first derivative of the function. Okay, so the first derivative of the function measures the rate of change of the original function. So it measures how the function changes as x increases or decreases. Okay, so we usually write the notation as f prime of x. Okay, and usually the magnitude and the sign of the derivative can give us a glimpse and an idea about how the function behaves at that point. Okay, so if f prime of x is greater than 0, so if it's positive, the function is increasing. Okay, so that means that on our visual graph here, we're going to visually identify where on the graph our function is increasing. And by doing so, we're able to find the interval of which the function is increasing. Okay, so you see here that at x equals 0, the function is decreasing, and it hits x equals 1, and it changes from decreasing to increasing, and then it starts increasing from 1 to 3. Okay, at 3, it starts to decrease again, and it starts to increase at 5 or 4. And at 4 to 6, it increases more. Okay, so the open intervals on which the function increases are, so function increases on the open interval on 1 and 3 and 4 and 6. Okay, so these are open intervals that the function increases on. So you see here as x increases, y increases on these intervals. Okay, so part B asks us to identify the open intervals where the function is decreasing. Okay, so if the function is decreasing, that means its derivative is negative. That means that the function is decreasing. Okay, and you guys know that another very important aspect about the derivative is if the function is equal, the derivative is equal to 0, we have a horizontal tangent, and that means that we have a min, max, or saddle point. But that's beyond the scope of this question so far. So let's identify the intervals on which the function is decreasing. So the function is initially decreasing at x equals 0 to 1, and it's also decreasing from 3 to 4. Okay, so these are the intervals. Function decreases on 0 to 1, and what did I say again? 3 to 4. Okay, so these are the open intervals that the function decreases. Okay, now let's talk about what concave up and concave downward mean. Okay, so what it means by concave up and concave down is that the function either is concave up, so it is curving upwards, or is curving downwards. Okay, that's what it means by concave up and concave down. And let me draw you guys an illustration of what a concave up function looks like. So a classical example of a concave up function is a upwards facing parabola. So this is a concave up parabola, and this means that the second derivative of the function is greater than 0. Okay, so function concaves up. Okay, so visually looking at this graph, we can see here from 0 to 2, the function is concave up. As you can see here, it's curving upwards. All right, and that's the only area on this graph that concaves up. So that means that function is concave up on 0 to 2. Okay, so what does it mean by concave down? It's the opposite of concave up, which states that the function is facing downwards. Okay, so if I were to draw another one, it'll be a classical example is a downward facing parabola, or a parabola with a negative coefficient, leading coefficient. Okay, so that means that the second derivative of the function is negative. Okay, and the function is concave up or concave down on 2 different intervals. So it's concave down on 2 to 4, and it's also concave down from 4 to 6. So it's actually just concave down on 2 to 6. Okay, cool. All right, finally E. All right, so now we need to talk about what a point of inflection is. Okay, so a point of inflection is a point on the graph on the function where the function changes from concave up to concave down. Okay, so that point is where the second derivative is equal to 0. Okay, x is point of inflection. Okay, so in the first derivative, when the derivative is equal to 0, that tells us that the function is neither increasing or decreasing. It's doing neither. Okay, so in the same way, when a derivative is equal to 0, it changes from increasing to decreasing. Okay, as you guys can see here, here's a pattern. So the function is decreasing, and here is where there's a horizontal tangent, and it switches from decreasing to increasing. Right, when the derivative is equal to 0, it's increasing. The derivative is equal to 0 here, and it starts to decrease again. So in the same way that there's a pattern between increasing, decrease, and where the derivative is positive, and then the derivative hits 0, and then it goes negative. In the same way, the second derivative also acts the same. So when there's a point of inflection, when the second derivative is equal to 0, the second derivative changes signs from either positive to negative or negative to positive. And that signifies to us that there's a point of inflection. Okay, so on this graph here, there's only one point of inflection, right? Because there's only one point on the graph where it switches from concave up to concave down. And that's where x equals 2. Okay, so x equals 2 is a point of inflection. Okay. So other than that, the solution is correct. And you guys can instead of looking at the graph and visually identifying it, you guys can just calculate the derivatives and try to understand the behavior of the derivatives in relation to the original function. Okay, but other than that, the solution is correct. Good work. All right. All right, so the next question asks us to graph these complex numbers and sketch z1, z2, z1 plus z2, and z1 times z2, okay, on the same complex plane. So the complex number has two different components to it, okay, and I'll describe what it'll look like on a complex plane. Okay, so we have what we call real numbers, right? So the real numbers are all of numbers on the real number line. So we have the natural numbers, the integers, the rational numbers, and the irrational numbers. Okay, so a complex number is the addition of a real number component with what we call the imaginary number. Okay. Okay, and that equals a complex number. Okay. So what is an imaginary number? So an imaginary number is basically the number I. And the number I represents the square root of a -1. Okay, so before, we could never even square root -1 because the square root -1 does not give us a real number solution. However, mathematicians have created and made the imaginary number I to circumvent this rule. So because of that, now we have what we call complex numbers. Okay, so if I were to draw the real number line, all right, so here's the real number line. I'll just draw it out. So this is our real number line. Okay, so real number line. Okay, here's our real number line. So the imaginary number line is a vertical line that's perpendicular to the real number line. Okay, so if I were to draw this, increase it. Okay, so this vertical line is what we call imaginary numbers. Okay, and they contain all the imaginary numbers. Okay, that means that if the real number line contained like 1, 2, 3, 4, and like -1, -2, and so on and so forth, the imaginary numbers will be I, 2i, 3i, -I, -2i, and so forth. Okay, so we have created a coordinate system for the imaginary numbers plus the real numbers. Okay, so a complex number exists in each of these quadrants. Okay, so a complex number will exist here and here and here, right? So only real numbers exist on the horizontal axis, imaginary numbers exist on the vertical axis, and if you combine them together, you get complex numbers. Okay, so that's what a complex number is, and they gave us two complex numbers. So they gave us z1, which is equal to -1, which is the real number component, plus I, the imaginary component, and z2, which equals to 2 minus 3i, with 2 being the real number component and 3i being the imaginary number component. Okay, so what they're asking us to do is to sketch or to graph z1 and z2, and to sketch or graph the sum of z1 plus z2 and the product of z1, z2. Okay, so I'll run you guys through each of these. And the last thing I want to note is that I squared is equal to -1. And that will come in handy in the last, in the product of the two imaginary numbers. Okay, so let's first write out what z1 is, which is -1 plus I. And let's write out what z2 is, which is 2 minus 3i. Okay, so first let's find the sum between these two numbers. Okay, so when we're finding the sum between these two numbers, we're going to add together the real number components and also the imaginary number components. So if we're adding z1 and z2, okay, so here's z1 and here is z2. We change it into this format to make another complex number. So the sum of complex numbers is another complex number. Okay. I minus 3i. Okay. So this is going to equal 1 minus 2i. Okay. So what about z1, z2? Okay. z1, z2 times z2. All right. So it's going to be kind of like expanding a factored form of a quadratic function. Okay, so you're going to use the FOIL method or whatever method you choose to expand this. Okay, so -1 times 2, right, plus 1 times 3i, okay, plus I times 2 minus I times 3i. Okay, so this is going to equal -2. This is going to equal 3i. This is going to equal 2i. And remember what I said above? I squared is equal to -1, right? So we have -3i squared here, right? So if we keep writing, we're going to simplify this. So it's -2i plus 5i minus 3i times I squared, which is also -1. And we get 1 plus 5i. Okay. So the product of two complex numbers is also a complex number. And the only difference here is if you had a difference of squares factored form. If you had a difference of square factored form, the imaginary number component would cancel out. But that's a niche rule. So now that we have each of these complex numbers, we're now going to graph them. Okay, so let's zoom out a bit here and let's put down an axes. Okay, here's my axes. Here's my real numbers, and here's my imaginary numbers. Okay, so we're going to put here the greatest one is 5i, right? And here's I. That's 2i, 3i, 4i, and 1, 2, 3, 4, and I think we need negatives too. -1, -2, -3. Do we need negative i's too? So -i, -2i, and -3i. Okay. So now that we have labeled out our axes here, we're now going to graph. So let's graph Z1 first. Okay. So Z1 is going to be red. So Z1 is -1 plus I. So -1 is here on the real number line, and I is over here. So Z1 is over here. Okay. All right. Z2 is 2 on the real number line, so it's here, and -3i on the imaginary line, so it's going to be here. So Z2 is going to be here. All right. Z1 plus Z2 is 1 on the real number line, and -2i down on the imaginary line, so it's over here. And finally, let's pick another color. Okay, so Z1 times Z2 is 1 on the real number line and 5i on the imaginary line, so it's over here. Okay, so that is how we graph it, and that's how we calculate the addition or the product of real or complex numbers. And calculating the difference between complex numbers is also similar to adding, but calculating the division of complex numbers is a little bit more difficult, and it has to do with using conjugates to simplify your denominator. Okay, but we'll cover that in a later lesson. So this solution is correct. Nice stuff. Cool. All right, let's move on to question number 3. All right, so find the critical numbers of the function h of x equals sine squared x plus cos x, where x is between 0 and 2 pi. Okay. So before in the first question, I described the first derivative and the second derivative. Okay. So what the critical point is referring to is when the derivative of a function is equal to 0. And when the derivative of the function is equal to 0, it signifies to us that our original function at that point has a horizontal tangent. So it's neither increasing or decreasing. Okay, so that's what a critical point means. So in this case, we're going to need to derive this the sine squared x plus cos x function and then set it to 0 and find the values of x that make it equal to 0. Okay, so, and another thing is that we need to be wary of the restrictions on x. X can only be greater than 0 and less than 2 pi. Okay, so here's h of x. I'm going to write it again. H of x is equal to sine squared x plus cos x. Okay, so if you don't remember your derivatives, the derivative of sine x, so if this is f of x, okay, let me write this in red. Maybe that'll be better. So if f of x equals sine x, then the derivative f prime of x is equal to cos x. And if f of x is equal to cos x, then the derivative is equal to negative sine x. Okay, so we're going to be using these derivatives to help us calculate this function. Okay, so the derivative of h prime of x is going to be the derivative of this function and this function. So using the chain rule here, we see that this is a function of a function. So we're going to derive the outside function first. So it's going to be 2 sine x. And then we're going to derive the inside function, which is sine x, which is going to be cos x. Okay, and we're going to derive cos x, which is going to be negative sine x. Okay, so this is the derivative of our original function. All right, next, what we want to do here is I'm going to factor out sine x. All right, and if I factor out sine x, we get 2 cos x minus 1. Okay, and here we're going to find the values of x that make it equal to 0. So we're going to set h prime of x equal to 0 and solve for the values of x. Okay. So to solve for the values of x, we need to find the values of x that make sine x equal 0, or the values of x that make 2 cos x minus 1 equal to 0. Okay, so one is sine x equal to 0. So sine x is equal to 0 when x is equal to 0 or pi. Okay, so how about 2 cos x minus 1? So we can rearrange this to write it as cos x equals 1 over 2. And now we need to find the values of x that make it equal to half. So the values of x that make it equal to half is pi over 3 and also 2 pi over 3, I think. I could be wrong. Oh, 5 pi over 3. Yeah, it's negative on the other side. Okay. So now that we have found the values of x that make this derivative equal to 0, we have found the critical numbers of our function. So the critical numbers are pi over 3, 5 pi over 3, and pi. Okay, and I excluded 0 because of the restrictions that are on x. Okay, so that is how you find the critical numbers of this function in particular, and in general that's how you find the critical numbers of any kind of function. You find the derivative first, you set the derivative equal to 0, and you solve for the values of x that makes it equal to 0. Okay, so other than that, the solution is correct and we can move on. All right, so the next question reads, find the slope of the tangent line to the parabola y equals 4x minus x squared at the point 1 to 3 using the limit definitions of a derivative. And there are two different limit definitions of a derivative. The first one reads that the derivative, let's say dy over dx, for example, is equal to the limit as h approaches 0 of f of x plus h minus f of x. So it's calculating the limit of the function, the difference between x plus h and the function as h approaches 0. So this will help us find the derivative. The second definition is somewhat similar and asks us to find the limit as x approaches a, right, of f of x minus f of a, x minus a. Okay. So these are two different ways of calculating the derivative at a certain point. Now, the other thing that we need to note here is that these will give us the derivative, right? But to find the slope of the tangent line at point 1 to 3, we have to sub x equals 1 into our derivatives. So once we find the derivative using either definition, we have to sub in x equals 1 to find the slope of the line at that certain point. So the derivative gives us the slope of the line at every point of the function. Okay? All right, so let's first use the first definition. Okay? So the first definition asks us to calculate the derivative using this definition. Where f of x is equal to 4x minus x squared. Okay, so this limit's going to be, so we're going to calculate 4x, f of x plus h, so that's going to be 4x plus h minus x plus h squared minus f of x, which is 4x minus x squared divided by h. Okay, that's equal to the limit as h approaches 0 of 4x plus 4h minus x squared plus minus 2xh minus h squared minus 4x minus x squared, okay, divided by h. That should be plus. Okay. Oh, no, that should be, this should be minus and this should be plus. Okay. So we see we can cancel out some terms. We can cancel out 4x and x squared. So we're left with the limit as h approaches 0 of negative h squared minus 2xh plus 4h, I think. Yep, divided by h. We can cancel out h from the bottom and the top, the numerator and denominator, and we get limit as h approaches 0 of h minus 2x plus 4. Okay, now we're going to sub in h as h approaches 0. So we're going to sub in 0 here, and all we're left with is 4 minus 2x. So this is dy over dx. And we want to calculate the slope at point x equals 1. So di over dx of 1 is equal to 2. Okay, so that's the slope of the tangent line. All right, let's use the second definition. Okay, so the second definition asks us to calculate the limit. Okay, oops, let me just do this. Dy over dx of the limit as x approaches a of f of x minus f of a divided by x minus a. Okay, let me make sure that's correct. Where f of x is equal to 4x minus x squared. Okay, so if we were to plug in f of x and f of a, we have this 4x minus x squared minus 4a plus a squared x minus a. Okay, so now here we want a to be whatever point we're trying to calculate. So x is going to approach 1 in this case. So x is going to approach 1. So we have 4x minus x squared minus 4 plus 1 divided by x minus 1. And then we have here the limit as x approaches 1 of negative x squared plus 4x minus 3 divided by x minus 1. We can factor this, the numerator at the top, to be negative x minus 3 times x minus 1. So you guys can pause the stream, and you guys can calculate you guys can factor it. You guys can just use the direct method of factoring this. All right, and at the bottom we have x minus 1. And if we cancel out these factors, we have, in the end, limit as x approaches 1 of 3 minus x, which is equal to, if we sub in 1, 2. So that's our slope. Therefore, now we can calculate the slope of the tangent line because we have found the slope. And now we can find the equation of the tangent line, okay? So the equation of the tangent line, if we have y equals mx plus b, where m is the slope and b is the y-intercept, we have the slope to be 2, and we just need to calculate the y-intercept. So we're given a point which is 1 to 3, which is on the line, so we're going to use that. So sub in 1 and 3, and what do we get? We get 3 equals 2 plus b, and b is equal to 1, and therefore y is equal to 2x plus 1. Okay, so that is the equation of our tangent line, and now we're going to graph it. So first we're going to graph the parabola. So this is the parabola here. It has zeros at 0. It has zeros at, if we factor out x, we have x and 4 minus x. It has zeros at 4 and 0, I believe. And the tangent line is going to be tangent to the point on the graph 1, 3. Okay, so the reason why we call tangent line, because tangent means that it is only touching one point on the graph, which is 1, 3. Okay, so that's the graph of the line here, and we calculate the equation of this line by finding the slope using either limit definition and then using the line equation to find the y-intercept. Okay, so other than that, the solution is correct, and we can move on. Good job. Okay. Whoops. Okay, let's move on to question number 5. All right, what is the limit of sine x over x as x goes to infinity? So they want us to calculate this limit as x approaches infinity of sine x over x. Okay, so in the last question we used direct substitution, and here we're going to try to use direct substitution, right? So we're going to directly substitute the n, so sine of infinity, right, divided by infinity. Now the reason why we can't calculate this limit is because the sine function is a periodical function, so that means that it cycles between values, okay? And because of that, we're not able to ascertain what the limit of sine of infinity is, and because of that, we're not able to evaluate what the limit of this function is, okay? So instead, we're going to need to use a different method of calculating the limit of this, okay? And the method that we're going to use is what we call the squeeze theorem, okay? So the squeeze theorem is very easy, and it has two conditions, okay, to find the limit of our said function. The first one is if we have a function, let's say f of x that we were trying to calculate the limit of. So let's say that we're trying to calculate the limit as x approaches a value a of f of x, okay, and we're not able to calculate it. So we can calculate it if we're able to find two other functions, let's say g of x and h of x, where the function is in between, the function's range is in between g of x and h of x, where g of x and h of x are functions. Okay. So the first condition is that our original function has to be, and this is where the name comes in, squeezed between two different functions. So there was one function that was always going to be less than or equal to our original function, and there's also another function that's always going to be greater or equal to our original function. Okay, so we can define these functions in anything, but as long as we find these two functions and the second criteria holds, then we're able to find the limit of our original function. So the second criteria is if the limit as x approaches a of g of x and the equals limit as x approaches a of h of x. Okay, So as long as the limit of x approaches a of g of x and the limit of x approaches a of h of x is the same, then the limit as x approaches a of f of x equals the limit, and let's say equals L, okay? So let me explain the second criteria again. So let's say that the limit of g of x as x approaches a is equal to a certain value. If the limit of x approaches a of h of x is the same, then by the squeeze theorem, we know that the limit of x approaches a of f of x is also the same. So we're going to employ the squeeze theorem, or what we call it the sandwich theorem, to our question here. Okay. So first, what I want to do is that I want to sandwich sine of x between two different functions, and we're going to define our functions as such. So the function that's always going to be less than or equal to sine of x is going to be -1, right? And the function that's always going to be greater or equal to our original function is going to be +1. Okay, so that is the definition of the range of the sine function, right? The sine function is always between 1 and -1, right? But we've just defined functions as -1 and 1, right? So now our original function is sandwiched, okay? So now to manipulate this inequality to get our actual function, we're going to divide all sides by x. So if I divide all sides by x, then we see here that sine x divided by x is also sandwiched between -1 over x and 1 over x. Okay? Now, we're going to calculate the limit as x approaches infinity of these two outside functions. So we calculate the limit as x approaches infinity of -1 over x. We get that equals to 0, right? Does that equal the other outside function as x approaches infinity of 1 over x? Yes, it does, right? So if I plug in infinity here, anything divided by infinity is equal to 0, and regardless of whether or not it's negative or positive. Okay? And because of that, therefore, the limit as x approaches infinity of sine x over x is also equal to 0. So by using the squeeze theorem, we're able to bypass any algebraic technique or direct substitution to find the limit of our function. And I would say that the squeeze theory is very useful for these kind of functions where there's a trigonometric function at the top. And it's just in general very useful for these kind of functions. Okay, so other than that, this solution is correct. Oops. Good job. Okay. Okay, and the last thing that I want to note is that if the limit of the outside functions are not the same, then that means that the limit, you cannot calculate a limit of the original function. You might need to find different functions to sandwich between. Okay. All right. So the next question reads: how do you find the remainder when 3x to the power of 4 plus 2x cubed minus x squared plus 2x minus 9 is divided by x plus 2? Okay. So the junior tutor here, they used synthetic division. So I'll be using synthetic division here, and also I'll be using long division, okay? And they're basically the same technique, but they're just written out differently. Okay, so what is long division or synthetic division, okay? It is like kind of like regular division where we're trying to reduce a polynomial or dividend into a quotient. Okay, so by reducing it, we're able to figure out whether or not the divisor is a factor of our dividend, okay? So in terms of polynomial division, if the factor is indeed, if the divisor, which is a potential factor, is indeed a factor of our polynomial, then that means that the remainder of the function or the division is going to be 0. Okay? So in long division, you draw a long divisional bracket and you include your polynomial that you're trying to divide, which is 3x plus 4 times 2x cubed minus x squared plus 2x minus 9. And treat each of these terms as digits of the number, for example, and treat each of these terms as digits, okay? So let's say that this is a 2-digit divisor and this is a 5-digit dividend, okay? So now you want to try to reduce the first 2 digits, right? So you see here that what are we supposed to multiply x plus 2 with to reduce and get rid of 3x to the power 4 and 2x cubed? Okay, we can multiply our divisor by 3x cubed. Okay, so if you multiply our divisor by 3x cubed, we get 3x to the power 4 plus 6x cubed. And if we subtract this, we get negative 4x cubed. So in the same way in normal division, you drag down a digit. In this way, we're also going to drag down the next term. So now we want to reduce this, right? So to reduce that, we're going to multiply by negative 4x cubed. So if we multiply by negative 4x squared, we get negative 4x cubed minus 8x squared. And if we subtract, we get 7x squared. Okay, now we drag down our next digit, our term, and we reduce it again. So that's going to be 7x, and that's going to be 7x squared plus 14x. We subtract, and we get negative 12. And now we drag down our last digit, and we have negative 12x minus 9. And to get rid of the 12x, we're going to multiply by negative 12, and we get negative 12x plus 24. If we subtract this, we get 15. Okay, so that means that 3x to the power 4 plus 2x cubed minus x squared plus 2x minus 9 is also equal to x plus 2 times 3x cubed minus 4x squared plus 7x minus 12 plus 15 over x plus 2 is our remainder. So our remainder is 15. Okay, so that's one way we can do it. The other way is called synthetic division, and it's the same method, but it's in a different kind of convention. So instead of writing out the polynomial, we're going to write out the coefficients of the polynomial. And instead of writing out the divisor as it is, we're going to write out the 0, or the solution to the factor. So the solution to the factor is x plus 2 equals 0, so x equals negative 2. So in our divisional bracket, we're instead going to write out upside down divisional bracket. Our divisor is going to be negative 2, and we're going to write out the coefficient of each term in our polynomial, which is 3, 2, negative 1, 2, and negative 9. Okay, so the way that synthetic division works is that we're going to drag down our first term, multiply it by our divisor, and then add it to our next term. And we're going to drag down, add, drag down, add. Okay, so if we drag down 3 and multiply it with negative 2, we get negative 6. So negative 6 here. And now we're going to add 2 to negative 6, which is going to be 4. Now we're going to times negative 4 to negative 2. And that's going to give us negative 8, or 8. And we're going to add these two together, which gives us 7, and so on and so forth. So this is going to be negative 14. And that's going to be negative 12. And this is going to be 24. And this is going to be 15. Okay, so if you did your normal long division correctly, then these quotient here, this quotient here is going to be the same as this quotient here. Okay, so now the last thing to note is that our quotient is 1 degree less than our polynomial, right? So if this is x to the power of 4, this is going to be x to the power of 3, right? So if this x to the power of 3, this is x squared, x, and our constant here, and this is x3, x squared, x, and our constant, then here is our remainder. Okay, so that's how you read the synthetic division, right? So your quotient here is going to be 1 degree less than your polynomial, right? So then the last number here is going to be your remainder. So remainder is equal to 0, then you know that your divisor is a factor of your polynomial. But in this case, it's not, and the remainder is equal to 15. So other than that, the solution is correct, and we can move on. Okay. All right, so the next question reads, what are the factors of g squared minus 32g plus 256? Okay. So we can, in previous lessons, I covered a lot about the cross multiplication method of factoring. Okay. And I really try to emphasize the fact that practice makes perfect, right? And you're able to practice and recognize patterns within your function, you're able to really do these factoring problems quickly and in your mind. Okay. So here's one pattern that we want to recognize here. Okay, so even before we jump into it, we recognize that our first and third term are perfect squares, right? So if we write out our function here, sorry about this, write our function here, we have g squared minus 32g plus 256. So I recognize here that the first term is a perfect square, which is d times g, right? And the third term is also a perfect square. It's 16 times 16, right? So here's a pattern that you want to notice. When you notice that your first and third term are perfect squares, then you might have a factoring question that is basically a perfect square factor, or a perfect square trinomial. Okay, so a perfect square trinomial takes the form as such, and the junior tutor describes it here: a squared x squared plus 2abx, or sorry, minus 2abx plus b squared. So this is the form that a perfect square trinomial takes, where the first term is a perfect square and the last term is a perfect square. And you find yourself having this kind of pattern where the middle coefficient is equal to 2 times ab, then your factors are just a minus b squared. Or I should write ax minus b. Okay? So here, we see here that g squared is a perfect square, right? So this is we can write this as 1 squared g squared minus 32g plus 16 squared, right? All right, so that means that a is equal to 1 and b is equal to 16. So then we can rewrite this as such again, right? So we can rewrite this as 1 squared g squared, right? So what about our middle coefficient? Is our middle coefficient the product of 2 times a times b? It is, right? 32 is the product of 2 times 16 times 1 g plus 16 squared, right? If we write it like this, then we know that our factors are g minus 16 squared. And there we go, right? And if I were to write this using the cross multiplication method, just to re-emphasize this, then this would be g times 16 times negative 16. If we cross multiply this together, we get negative 16g minus negative 16g, and what we get? Negative 32g. So therefore, the factors of this is g minus 16 times g minus 16, which is g minus 16 squared. Okay, so these are one of the patterns that you need to recognize when you're factoring, because if you recognize these patterns, then it's very easy for us to factor this, right? You just find the perfect square, or you find the value of the perfect square here, and then you write it in this form. Okay, so other than that, the solution is correct. And the other pattern I want you guys to recognize is the difference of square pattern, right? The difference of square pattern would be very self-presentable, but it's very easy to see. But other than that, the solution is correct, and nice work. Okay. All right, moving on to question number 8. So form a polynomial whose zeros and degrees are given. Okay, so the way that zeros and factors are related to each other is that the zeros are the solutions to when the polynomial is equal to 0. Okay, so when they give us the zeros of a polynomial, we are able to find the factors of the polynomial. Okay, so let's first find the factors of the polynomial, and then let's talk about what multiplicity means. Okay, so the polynomial here has zeros of -5 and also of -1. So the zeros are -5 and the 0 is also -1. So to find a factor, all we have to do is isolate or move the constant to the other side. So we move the constant to the other side, we get that x plus 5 is one of the factors, and we also know that x plus 1 is the other factor. Okay, so the other key piece of information here is that the polynomial is of a degree 3. Okay, so right now we have 2 factors, so if we were to write it out as such, and we were to expand it, we would see here that we do not get a polynomial that is of degree 3, right? And this is where multiplicity comes in. So multiplicity basically describes the degree of power of our factors, okay? So when we have a degree 3 polynomial, the multiplicities of your factors have to add up to the degree, okay? So if we have a degree of a polynomial, that means that the multiplicities equals the sum of the multiplicities, okay? So it equals the sum of the multiplicities. So that's what multiplicity means, and multiplicity basically means multiplicity. And multiplicity basically means the power of each factor. So we see here that with a multiplicity of 1 for each factor, we have a second degree polynomial. Okay, but here we have a third degree polynomial, and a way to check that your multiplicities are correct is if your multiplicities add up to 3. So in this case, our factor of x plus 5 has a multiplicity of 1, and our factor of x plus 1 has a multiplicity of 2. So with that in mind, we can rewrite our polynomial as this. And if we were to expand this, we would get x plus 5 times x squared plus 2x plus 1. And if we were to expand this further, we get x cubed plus 2x squared plus x plus 5x squared plus 10x plus 5. And we simplify it, we get x cubed plus 7x squared plus 11x plus 5. And that is our polynomial given the multiplicity and degree and the zeros. Okay, so always make sure that your multiplicities add up to the desired degree of your polynomial. And if it does, that means that you have the correct polynomial, or that's one of the indicators that you have the correct polynomial. Okay, so other than that, the solution is correct. Good work. And finally, let's move on to the last question, which is another question about long division. So here they're asking us to find the remainder again. And in this question, I'm just going to go through it. And you guys can pause the stream and you guys can try to run through either a solution of using synthetic division or long division. I'll use both in the end, but I want you guys to pause the stream and try to do this question yourself while I work on it myself. Okay? So if f of x equals 2x cubed minus 12x squared plus 11x plus 2, and we have our divisor as x minus 5. Okay, so the first one is 2x cubed minus 12x squared plus 11x plus 2 divided by x minus 5. Okay, so the first term here is going to be x squared. So if I multiply this by x squared, we get x squared times x is going to be 2x cubed minus 5x squared, right? If we subtract this, whoops, we have negative 7x squared. All right, we drag down our next term, which is 11x. And we want to get rid of the 7x squared, so we're going to multiply our divisor by 7x, or negative 7x. We get negative 7x squared minus 35x. If we subtract it, we get 24. Nope, we don't get 24. That's wrong. We get 46x plus 2. And to get rid of 46x, let me just see that if I did this correct here. This should be 10x, my bad. Okay, I already made a mistake. Always make sure you check that you multiply everything correctly. Okay, so this is not correct either. Okay, so this is going to be 10x squared. Okay, and that's negative 2x squared plus 11x. And negative 2x. We get negative 2x squared minus plus 10x. Okay. Add it together, we get x plus 2. Okay. And then finally, we multiply by 1. and we get x minus 5, and we subtract, we get 7. So 7 is our remainder if we use long division, okay? So the other way is also synthetic division. So instead of writing out our polynomial, we're just going to write the terms of our coefficients. So 2, negative 12, 11, and 2. And we're going to write out the 0 of our divisor, which is 5, and we're going to drag down 2 here, multiply 5 to 2, and add it to negative 12, so that's 10. That's negative 2. Then we add negative 10 again, that's 1, and 5 is 7. Okay, so if this is x cubed, this is x squared, so our remainder is 7. Whoops. Okay, so the remainder here is 7. Okay, so now we have used long division and synthetic division to solve our problem here, but there's also another way of calculating the remainder of our division, or long division, okay? So usually when you're trying to figure out whether or not your divisor is a potential factor, you want to use long division, but there's a much simpler way of doing this, okay? And the simpler way is to simply plug in the 0 into your polynomial. And if you plug in the 0 into your polynomial, what's the definition of a 0? The definition of a 0 is the value of x that makes your polynomial equal to 0. So if you plug in the 0 of a factor, that means that the polynomial is going to equal 0. Okay? But however, if you plug in the potential factor and the potential 0 into your polynomial and you don't get your polynomial equal to 0, that means that your factor is not actually a factor, and also that you find a remainder. So let's run through the steps of what the junior tutor did. Okay, so the junior tutor here, they found the 0 of x minus 5, right? So the 0 of x minus 5 is x equals 5. So that's your first thing that you need to do. So you find the 0, and next you plug the 0 into your function. So you plug f of 5 into your function, which is going to equal 2 times f to the power 3 minus 12 to the times 5 to the power squared plus 11 times 5 plus 2. Okay? And if we were to simplify this, we would get 250 minus 12 times 25, which is 300, plus 55 plus 2. Okay, and if we were to simplify this, we would get negative 50 plus 55, which is 5 plus 2, which is equal to 7. And we have found our remainder. And we have double checked it and triple checked it using synthetic division and also long division. So the answer is C. Okay, so this solution is correct, and we have done it in 3 ways. All right, so that wraps up today's lesson on functions and also algebra. If you have any other questions, please submit them to OneClass, and we'll get to them as soon as possible. But until next time, I'll see you guys later, and have a good night, and I hope you guys learned something. Bye, guys.